this begins EE 544 on Thursday, March 27, 2014.
Thank you very much. Good morning. Good afternoon, everybody. Let's continue our discussion from last time. We started talking about power amplifiers. And again, as I told you, we are going to be looking at each one of these major components of a transceiver design from a circuit point of view, and we analyze the circuit so that we understand the performance of the circuit. From the transmitter side, we are only going to be looking at what? The power amplifier. We are only going to be looking at the power amplifier. Then we will switch to the what? To the receiver side, where we study the low noise amplifier, the mixers, the oscillators, the synthesizers, and so on and so forth, all of these things. In the transmitter side, only the power amplifier. The power amplifier, again, as I told you, the purpose of the power amplifier is to deliver the right amount of power to the antenna, to deliver the right amount of power to the antenna, but at the same time preserving all the characteristic or all the specifications of the what? Of the modulation techniques that you are using, which means what you need to make sure that your transmission or your emission is confined within the band of interest, within your channel, clear within your channel. You are not going to exceed that range. This is, again, the modulation process, the IQ. By the way, in here, it shows that the modulation is taking place in one step. Could it go into multiple steps? Okay. In other words, could it go into IF and then what? And the RF and stuff? This is just a diagram here. And this is the power amplifier sitting here. We saw that we need to connect it to a what? To a magic network to try to reduce the amount of what? The amount of power being what? Being reflected. Clear? The amount of power being reflected means what? Means that you are going to lose it. The requirements, again, this from last time quickly, the output power depends on the system, the standard. The Bluetooth, for example, is 4 dBm, GSM is 33 dBm, wideband CDMA 27 dBm, and so on and so forth. All of these, the standards will specify the amount of power that you can use. Power gain, typically anywhere between 10 to 50 or 40 dBs, and so on and so forth. Efficiency, which is most important to us, we don't want to what? We don't want to, because remember, the power amplifier is going to convert the DC power to what? To RF power. We don't want a lot of what? Power being dissipated in the transistor. Actually, the ideal thing is that we want the power dissipated in the transistor to be equal to what? Zero. Are you following? To be equal to zero, so that the efficiency becomes what? Very close to being 100%. Clear? We want to convert the entire DC power into the RF power. We'll talk about that in a minute. Linearity, of course, is important, especially if the modulation technique has a variable envelope characteristics, like AM or like what? Like QAM or like a QPSK, all of these modulation technique, which suffers what? Again, as I told you, remember, even though we talk about QPSK, which is the modulation on the phase, but because of the transition that I showed you last time, there's a possibility that the amplitude will go through what? Will go to zero. So for a short period of time, you could have what? Amplitude variations. And with amplitude variations and nonlinearity, you are going to create the spectrum regrowth, which means what? You are going outside the band that you are assigned to. We talked about this, all of it last time, the impedance matching. Again, as I told you, you would try to minimize the amount of losses that the matching circuit is going to what? Introduce into your network. And of course, the power control, again, as I told you last time, this is only used for CDMA. If you are operating using FDMA or if you are operating using TDMA, power control is not a big issue. Why? One more time. Why in TDMA the power control is not a big issue? Because in TDMA, every mobile unit or every base unit, it will be what? It will be transmitting using separate time slots. So it's not at the what? At the same time, but it's multiple time slots. So the effect will be less than the effect if you are using a CDMA. The parameters of interest that we defined last time, the power efficiency, which is the ratio of the RF power divided by the DC power. There is another definition of the efficiency, which is called what? Power added efficiency, which is defined as what? The P out minus P in. Both of these are what? RF powers. P out minus P in divided by what? Divided by the DC power. If you replace this by this, you will end up with what? The power added efficiency equal to what? 80 times 1 minus 1 over GP. And if the power gain is relatively high, then the power added efficiency is almost the same as the drain efficiency. This one sometimes called the what? The drain efficiency. Of course, if you are using MOSFET. Oh, yes.
Yeah. If I'm using a constant envelope modulation and the PA is operating in the nonlinear region, will it be creating a out-of-band experience?
If you are, one more time, repeat, you went too fast on me. You went too fast on me.
If I'm working with constant envelope modulation.
So the question is that if my modulation technique was a constant envelope and you are operating in a what? In a nonlinear region, the effect will be minimal. The regrowth will be minimal. Why? Because the amplitude is what? Is fixed. It's not changing. The changing of the amplitude and because of the nonlinearity, results in what? Creating those sidebands. If the amplitude is what? Is fixed, those sidebands will be what? Will be minimal. Are you following with non-existence? Clear? You can afford to operate at what? At high efficiency.
And also for the non-constant envelope, if the PA is working in the linear region,
I need to, my dear, you need to be patient with me. Remote location students cannot hear you. The question is that if I am if I'm using a non-constant envelope modulation technique, but I'm working in the linear region of your power amplifier, then you are not going to create what? Those regrowth. It will not regrow again. Why? Because a linear system, which is what is going to be approximated if you are operating in the linear region of your power amplifier, does not generate new frequency components that were not present in the input. Always remember that. A linear system does not create new frequency components that were not available at the input. Clear? If the input does not have that frequency component will not show up at the output. Clear? Okay, good. Now, again, one of the performance measures as far as linearity is concerned, a lot of them regarding what? In other words, how do you know whether your system is linear or not? You check what? You check, for example, the ACPR, which is what? The adjacent channel power ratio. You check the what? The spectral mask. If your emission is within your spectral mask, that what? That's an indication that what? Everything is what? Linear. You are not getting those side growths. You check the 1 dB compression point. The higher it is, the what? The more linear the system is. You check the IIP3, the intercept point, third order intercept point. The higher it is, the more what? The more linear the system is. Clear? Okay, but always keep in mind, if you are operating in the linear region, it means that you are not utilizing the what? The efficiency of your amplifier to the what? To the maximum. And that I will show it to you in a minute, if you give me a minute. Can you give me a minute? Okay, I will show you that in just a second. Okay, a minute became a second. I don't know how it became a second. Okay, in any case, what type of power amplifiers we are looking at? We are going to be looking at two types of what? Power amplifiers. Clear? Again, remember, we don't have time to go into too much detail. So I'm trying to give you as much as possible. Okay, so we are going to go into what? Two types of what? Power amplifiers. The first one is what is known as a what? A current mode amplifiers. A current mode amplifiers. In these amplifiers, the transistor or the MOSFET is behaving as a what? As a constant current, which means what? It is not behaving as a what? As a switch. It is going to be operating in a what? In a saturation region, rather than what? Switching between what? Between, how many of you have taken 477? How many of you took any class in digital stuff? None of you? Okay, you know that the MOSFET has how many regions of operation? It has the what? The triode. It has the what? The saturation, and it has the what? The off. If you are operating your MOSFET in a what? As a switch, you are going from which mode to which mode? You are going to go from the off mode to the what? To the triode mode, without stopping, or at least just quickly going through what? The saturation mode. But if you are operating it as a what? As a constant current, as a constant current source, you are operating in which region? In the saturation region. Clear? As we'll see that in just a second. Here, the transistor, again, is acting as a transconductance block, and the classes we are going to be looking at in a minute, class A, B, and C. When we look at these in a minute, we will see that all of them is the same circuit. The circuit is the same, but the point where you bias your amplifier will what? Will determine whether it is a class A, or whether it's class B, or whether it's class C, and so on and so forth. Clear? Clear? The circuit is the same. The amplifier is the same. Okay. Then we are going to be looking at the switching mode power amplifiers. In the switching mode power amplifiers, we will see what? We will see that the transistor is actually acting as a what? As a switch. As a switch. On, off, on, off, on, off. Clear? Okay. And the classes that we are going to be looking at, class D, E, and F. And each one of them have a separate concept. But I need to show you each one of them in some detail so that you understand, and then if you are interested, you can go and learn on your own. Now, current mode amplifiers, the current mode power amplifiers, we will see they are better in terms of what? Linearity. When I say better in terms of linearity, means what? More linear. But they are not so good as far as the what? As far as the efficiency is concerned. Clear? Okay. And the mode, we will see that the class, whether it's mode A or mode B or AC, it depends on what is known as the biasing of the transistor and the what? Angle of conduction. Angle of conduction means what? In one cycle of a sine wave, in one cycle of the what? Of the RF signal, how much of it will the transistor be what? Conducting. During how much? If, for example, if it is conducting during 360 degree, what do we say? We say that the transistor is always what? It's always conducting. It's never going to be what? It's never going to be switched off. Did you get this or not? It's not going to be switched off, which I will show you in just a second. Okay. Now let's skip this page, and I will tell you why we skip it in this page. And we'll get to this in just a second. Don't write anything. I did this in the office, so that does not take too much time. Look at my handwriting. Is it nice? This is what happens when I am not rushed. When I'm not rushed, it's what happens. Handwriting becomes what? Clean. Let's look at the circuit first. Try to understand it carefully. I want you, first of all, to tell me what is the difference between this one and this circuit. What is the difference between this one and this one? In here, you see that there is a what? A resistive loading. Are you following me or not? In here, the resistive loading is here, whereas in here, I put a what? A high inductor. RFC stands for what? RF choke. I will see why they call it choke in just a second. Did you get my point or not? Cannot hear you. Let me ask you a question here. And by the way, this one is terrible. This one is terrible. Clear? That's why I'm trying to omit this one, just to explain to you this one. Let me ask you a question. Can you zoom in please a little bit? Okay. I want you to see this voltage, which is the voltage across the voltage at the drain. By the way, what are the terminals? Let's see if you remember electronic classes. What is this? Gate, source, drain. Which means what? This is a common what? A common source. Question. Is it possible that we design our amplifier a common drain or a common gate? No response. Yes or no? I will ask you this in the homework. Do you find the homework? I will give you examples in which you design the other way around. But in the class, we will look at what? The common source. Clear? Okay. I want you to see the drain. If the power supply is VDD, this is the power supply. This is DC. This is the one that will provide you with the DC power. One more time. What is the purpose of this guy? To convert DC power to what? RF power. Notice, by the way, what do you see at the input? What do you see at the input? You see two sources. One of them is the RF signal. That's the RF signal, the input, which means what? It's the output of the who? Of the modulator. Yes or no? Okay. But what is the other one? That's the biasing. Are you found the biasing of the transistor? Now, this is for simplicity. I am putting another source. You could also bias it from what? From the common source. From the same source. You can what? Put resistors here and so on and so forth. But we try to avoid using a lot of resistors. Why? A lot of resistors, when we get to the noise, the noise factor analysis, we will see more resistors means what? The noise factor will go what? Will go up. Clear? Oh. What is the voltage in here? Maximum. Maximum voltage in here is how much? Is VDD when the current is what? When there is no what? When there is no current. In other words, when the transistor is cut off, the voltage in here is a maximum of what? VDD. It cannot go more than VDD. Yes? No response. Okay. I want you to see this and to try to understand it carefully. We'll get to it in a minute. But let's jump a little bit. Do you see the VDS? What is the VDS? Is the voltage between the drain and the what? The source. The source being what? Grounded. So when we say VDS, is the same as saying what? The voltage at the drain. Yes? How come it's 2 VDD? How come the maximum is 2 VDD? It's not VDD. In other words, this voltage could be even higher than this one. In here, one more time. Could this voltage be higher than this one? It cannot be higher than this one. Are you following me on that? In here, could it be higher? This voltage here. Could it be higher than this voltage here? Yes, it could. Why? Because this voltage is what? What is this voltage? I forgot. Okay, I wrote here why. Why? It's what? It's equal to VDD minus L di of t dt. Do you agree? Is it possible that di of t dt is negative? Remember, it's a sinusoid. Are you following me or not? It's a sinusoid. Is it possible that in some interval the slope is negative? If it is negative, with the negative becomes what? Positive, resulting in this voltage being what? Higher than VDD. And that's the whole idea. Did you get my point or not? Yes or no? Okay, good. Now, let's understand the circuits first of all before we get into the detail of the analysis. Remember, this applies for what? Class A, Class B, Class C. The difference is what? Is the biasing. The difference is how I bias what? My transistor through this one here. Clear? What is the RFC? RFC is what? A very large inductor. When I say inductor means what? Means L is what? Large. Which means what? At DC, what is this behaving as? It's behaving as a short circuit, allowing the DC current to come through. The time is 13 o'clock. Did you get my point or not? Notice, by the way, I did not say the DC coming this way. Why? I don't want DC coming this way. I want this one to be strictly what? A sinusoid, an RF signal. And that is why I'm using a what? A blocking capacitor here, a coupling capacitor. Did you understand that or not? This is an AC coupling, which means what? AC signal will be coupled in here, whereas the DC will be what? Will be blocked. Now, for the AC, what do I want this to behave as? For the AC. For the AC means what? For the RF. AC means what? Alternating current means what? Means in the RF. What do I want this to behave as? I want it to behave as a what? As a open circuit, which means what? All the RF signal will come in here, from here to here. Did you get this or not? Yes or no? Now, notice, by the way, when you sketch the AC equivalent circuit, the AC equivalent circuit of this circuit, where would this point be? This point will be grounded, which means what? This inductor will be where? In here. Did you get this or not? And you might choose the value of this one to be grouped with any parasitic capacitor inside the MOS to behave as a tank circuit tuned to what? To the fundamental frequency. Did you get my point or not? Did you get my point or not? Okay, good. Now, I want you to see this circuit. Don't look at this one here first. This. What is this for? This one could be used as a matching circuit. Do you agree with me or not? That's the L matching circuit. Now, this one is behaving as a what? As a DC blocker, but it could also be used as part of what? As part of the matching circuit. Yes or no? Okay. Notice, by the way, if there is also an inductor here or a capacitor here, it could be a what? Could be a pi matching circuit rather than just an L. Are you losing me? Are you losing me? Tell me, what is this for? This is a tank circuit. If you look at this, this is a tank circuit. What do we need a tank circuit for? We will see in just a second that other than a class A, which means what? Class B, Class C, Class AB, the signal in here will not be a sinusoid. It will not be a sinusoid. And if it is not a sinusoid, What does it mean? It means that I have created harmonics. Are you following me or not? It means that we have created harmonics. Now, what do I want? By the way, this is a parallel tank. It does not have to be a parallel tank. You could have a series tank. But for the sake of argument, this is a parallel tank. What do I want? I want at the fundamental frequency, what do I want this to behave as? This combination. What do I want it to behave as at the fundamental frequency? I want to behave it as an open circuit. Why? So that all the RF will go to the what? To the load. The load is the antenna. Think about it this way. Yes or no? You are losing me. You are losing me. I can tell you lost me. Okay, let's see if you can answer me the next question. What about the other harmonics? What do I want this to behave as? The other harmonics, second harmonic, third harmonic, fourth harmonic. What do I want this circuit to offer? High impedance or low impedance? See, I told you you lost me here. I want what? I want high impedance or low impedance. I want to be very low impedance, which means what? I want this one to behave almost as a what? Short circuit, so that all the harmonics will come where? Here, rather than going to the load. Yes or no? Cannot hear you. We are struggling. Once we get to the circuit part, it means the struggle starts. Because most of you are what? How many of you are circuit type? None of you are circuit type. So you should help me here. You are sitting there doing nothing? Okay, so we are struggling. The struggle will continue. But I don't care. So we struggle, we struggle. Are you following me or not? Yeah, now, when we get to the class A in a minute, we will see that actually this circuit, this tank circuit, is not needed. In other words, you could remove it. It's not needed. You could just have a coupling capacitor to the load. This one will not do much to you. Why? Because this one, we will see that it's already what? It's already sinusoid. And since this capacitor is a what? Is an AC coupler. AC coupler means what? The AC will go through. Yes? What do we need the tank circuit for? We don't need the tank circuit for. By the way, keep in mind, this tank circuit, even though theoretically it will not introduce losses, but in reality it will introduce losses because there is some parasitic resistances in there. Are you following me or not? Yes or no? Okay, good. Now, let's see class A. Let's see if you can help. Did you understand the circuit? Okay. Did you understand, before I continue, did you understand why did I replace this resistor by an inductor? I want to increase the what? I want to increase the voltage in here beyond the what? VDD, allowing me a what? A maximum swing. The maximum swing, the more swing you have, the efficiency will go what? You will see it will become better. Did you get my point or not? So I replaced this resistor by what? An inductor. Clear? Okay, so I'm not going to go through this. I'm just going to explain this one. Now, let's see if you can help me here. This is the bias. Are you familiar with this? Or do I need to explain it to you? These lines, this is the characteristic of what? We call it the what? The output characteristics of the what? Of the MOSFET. Which is what are you sketching? VDS versus what? ID. Yes? Now, what do I call this? This line, what do I call it? The quiescent or the load line. Yes? What is the load? Which load is this? What is the slope of this guy? What is the slope of this guy? It's minus 1 over RL. You lost me here? Why? Why minus, first of all? The slope is negative? Don't make me lose my temper here. This is very simple. Is the slope negative? Okay, what RL are we talking about? This RL. Did you get this or not? This RL we are talking about. Clear? Okay, good. Now, what is the maximum voltage that it can reach? VDS to VDD. Yes? This one here is what? Is divided by RL. Are you following me or not? This is the maximum current. Where am I going to bias my transistor in a class A? This is class A. I'm going to bias my transistor in the middle of the load line, which means what? What is the quiescent point? The quiescent point is this point. This is the operating point. At what voltages? We need to understand the notation because we'll get to the analysis in a minute. It's what? VDQ, IDQ. What is the D stands for, first of all? Drain. Yes? And what is the Q stands for? The quiescent. This, don't confuse this with DC. In this case, as we'll see in class A, this is the DC value. We'll see that in just a second. But in general, it's not. Did you get my point? This is where you are operating. Now, what do? You extend a line in here. Same thing as line. What am I sketching? What is this? This is the RF signal on what? On the drain. It is around the what? The quiescent point. The quiescent, when we talk about the quiescent, is what? Static analysis. You understand that or not? This is the what? The RF analysis on top of the what? On top of the static. Did you get this or not? Okay, now answer me the following question. Where is it going to? It is going to all the way to what? VDD. Sorry, to VDD. Which means, what is this one from here to here? We call it what? A VDP. What is the P? The P is the what? Is the peak. Yes or no? Cannot hear you. That is the peak voltage. Is it the same as the fundamental in this case? In this case, is it the same as the fundamental voltage? You do understand we have fundamental and we do have what? Harmonics. Is this in here, in this example, is VDP the same as the fundamental? Yes, it is. Why? Because this is a pure sinusoid. Agree? Now, in here, I am making a slight approximation. What is the approximation? I am assuming that the saturation, are you familiar with the saturation voltage? The VDS saturation is approximately equal to what? 0. Because this one actually should go only to what? To this value. Did you understand that or not? But for simplicity, I'm assuming VDS sat, which is what? Typically, anybody? It's roughly 0.5 volt or something like that. Yes? Yes or no? I'm neglecting it so that I can show you the what? The full what? The full sinusoid. Clear? No response. Clear? Question. Will this voltage appear at the load? Will this voltage appear at the load? Yes, it will. Why? Because for AC, for RF, this behaves as a what? As a short circuit. This behaves as a short circuit. So whatever the voltage in here will be the voltage in here. Agree? Yes or no? Okay. Remember, by the way, do we need this? We don't need this in the tank circuit. Sorry. In the class A, do we need this one more time? We don't need this. Why? The signal here is already a what? A sinusoid. A sinusoid means what? It's only the fundamental component. No what? No harmonics. Clear? No response. Clear? Okay, good. Now, let's continue. Project this one onto the load line. What do you get? You get the current. Are you following me or not? You get the current. Question. This is which current? This is the current ID, which is this one. The current here. Yes? This is the ID current. Yes or no? Okay. Now answer me the following question first. How come it's the opposite direction? See this one here? This one increasing. The current is what? Decreasing. I'm not sure did you get this or not. In other words, I want you to see something here. Is there a 180-degree phase shift? There is a 180-degree phase shift because this is a common what? This is a common source amplifier. A common source amplifier produces a what? A 180-degree phase shift. Yes? Why is that? Let's understand why is that. Why is that? Is that because as you increase the voltage in here, as you increase the voltage in here, what will happen? What will happen? This one will be what? Will be conducted, but it's now, it's in the what? In the other direction. In the other direction, which means what? Current coming this way. Did you get this or not? Remember, this one will not pass any what? Any AC. Are you following me or not? So the current, it depends on the polarity. Either going this way or going what? That way. Did you lose me? Did you lose me? This one has no AC current in here. So where is the AC current going? The AC current is going this way or it's going what? That way, depending on the polarity. Clear so far? Now, I want you to see this and answer me the following question. Is it a sinusoid? Okay, what is this line? What is this dotted line? This dotted line is IDQ. Yes? Which is what? Which is the quiescent point. Yeah. Now, what is this point here? Approximately. What is it? It's IDP, which is what? Which is the peak. Yes? No response. Yeah. Now, is it almost equal to IDQ? Why? Because I am assuming that there is no clipping. There is no clipping. Is this a pure sinusoid or not? Now, in reality, will there be a little bit of a clipping? There will be a little bit of a clipping from top because this one does not reach all the way to here. Did you get my point or not? There is a little bit of clipping, but this one is almost equal to what? It's almost equal to this. Clear? Now answer me the following question. Will it also be equal to the DC current? It will also be equal to the DC current. Why? Because this is a pure what? A pure sinusoid. Clear? No response. Clear? Okay. Are you losing me? The circuit guy, you need to help me a little bit. Okay. Let's see if you can help me with the equation. What is the drain current? Can you tell me what is the drain current? How would you write the drain current? Okay. First of all, is there a quiescent point? This is the quiescent point, IDQ. Yes? Remember, when you do the quiescent analysis, is it AC or is it DC? It's DC. Are you following or not? It's DC. So this is what? The IDQ plus the what? The variation which is due to the what? To the RF. What is it? Is it a sinusoid? Now, what is the equation of this guy? Can you give me the equation of this guy? Just this guy. It's what? It's IDP times what? Cosine or times sine, whatever it is. Yes or no? Sine or cosine, doesn't matter, whatever. Yes or no? Okay. What is the VDS? What is the VDS? This VDS, the voltage between this one and this one. Same idea. It's the same idea. You have the what? The VDQ, which is the what? Which is the quiescent, plus what? Plus this one. The reason I wrote minus is because, remember, there's a 180 degree. So one of them is plus, the other one is a what? It's a minus. Doesn't matter. Clear so far? Yes or no? Now, let's see if you can help me. In a class A, what is the DC current? First of all, what is the IDQ? IDQ, because we are biasing the transistor in the middle, the IDQ is approximately equal to what? IDC. Why are we interested in the IDC? Why are we interested in the DC current? We are interested in the DC current because we need to calculate what is the DC power. What is the efficiency one more time? It's the RF power divided by what? The DC power. Can you tell me what is the DC power equal to? First of all, where is it coming from? The DC power, where is it coming from? It's coming from the VDD, from the source. Yes? What is the DC power? Let me jump a little bit. What is the DC power? VDD times what? IDC. Do we agree? What is this? This is Ohm's law. Guys, this is Ohm's law. VDD times what? The current. It's the voltage times the current. Everything is in DC. Clear? Clear? Now, I want you to see one more time. In class A, what is the DC current? The DC current is the same as what? The quiescent current. And it's also the same as what? Approximately is the what? Is the peak or the fundamental. Yes? Now, what is the DC power? The DC power is VDD times what? IDC. Agree? Okay. What is the RF power? Delivered to the what? Load. Let's see if you can help me. The RF power. At what? At what frequency? At omega naught, which is the fundamental. We don't have any harmonics. Explain to me where is this square root came from. It's the RF power. So we are taking the what? Roman square. So it's what? IDP times what? VDP. Each one is divided by what? Square root of 2, which is what? The VDP is what? What is the VDP? This is the VDP. Is it almost the same as the quiescent? And what is the quiescent? What is the quiescent value? VDD. I biased my transistor at VDD. Yes or no? So it's what? It's VDD times what? IDC. IDC is the same as IDP divided by what? 2. I divide one by the other, I get what? 50%. That's the maximum efficiency of a class A amplifier. 50%. Good or bad? Relatively bad. And notice, by the way, this is everything is theoretical. This is theoretical. This is only good on a piece of what? On a piece of pad under the camera. That's it. If you go and implement it, you will see efficiency roughly 25 to 30%. By the way, theoretically, let's see if you can tell me, what is the efficiency of this by inspection? Theoretically. Remember, this one reaches what? 2 VDD. Sorry, this one reaches what? 2 VDD. This one reaches what? VDD, which means the biasing will be where? VDD over what? 2. Yes or no? Which means what is the efficiency of this theoretically? 25%. It's even what? Half of this one. But if you implement this one, or if you implement this one, you will see that the efficiency you get, this one here, is roughly 30% or even a little bit lower, taking into account all the what? Parasitic problems, the resistance problem, and so on, fluctuations in the VDD, and so on and so forth. All of these types of problems. Clear? Clear? Can you show me the input characteristic? The input characteristic. By the way, input characteristic, what am I sketching? Are these input characteristic or output? What is the input characteristic? It's ID versus what? VGS. I will show you that for class B, and then I'll comment on class A. But did you get my point? Okay, good. Any question on this? Any question on this? Did you get it? Okay. We already talked about this. Yes? Okay. By the way, what is the power dissipated in the MOS? What is the power dissipated in the MOSFET? As what? As heat. Yes? What is it? It's the PDC minus the what? Minus the power fundamental, which is what? Which is the R of power. Remember, the efficiency is 50%, which means what? 50% is what? Is dissipated. Now, if you sketch, by the way, all of this, don't write anything. Just download it from the site. I will be posted. So if you sketch a diagram that shows what? That shows the output power. This is the what? This is the power dissipated. This is the actual what? This is the actual power. And you reach what? You reach a point here where it's the what? Where is the maximum power delivered, which is what? VDD square over what? 2RL. Yeah, what power here? When I say power delivered to the load, that's the fundamental power, the RF power. Clear? Clear? Okay. Now, another parameter which is also used in addition to the what? To the drain efficiency and the power added efficiency that we talked about earlier is what is known as the normalized power factor. The normalized power factor, also used widely in the design of power amplifiers. What is the normalized power factor defined? The maximum RF power delivered to the load divided by what? The maximum possible power. What is the maximum possible power? Is when you multiply VDS max times what? ID max. Both of them are what? Are maximum. Did you get this or not? Okay. What is the maximum voltage can there be? 2 VDD. Did you answer where the 2 VDD came from? 2 VDD came from this value. Yes? What is the maximum current? Also, maximum current is what? From here to here. That's the maximum current. Yes? So it's what? It's 2 IDP. IDP is the peak. So it's what? Peak to peak. So if you take this one, which we already derived, divide by this one, you will get what? 1/8, which is what? Which is 12, roughly what? 12.5%. Are you following me on? Good or bad? 12.5%. Again, it's a measure of how much power we can get from the MOS, considering the what? The IDVD boundaries. What does boundaries mean? Remember, by the way, once you go beyond the boundary, what will happen? Say that again? No, I mean, it's the voltage here. Once you go beyond the boundary, this to BDD, if you what? If you go beyond that, you are going to result in what? In a breakdown of the what? Of the transistor. Are you following me or not? So that's what it means by what? By the boundaries. Clear? Okay. So don't forget this. This one also is used. It's normalized power factor. They call it what? NPF. NPF stands for what? Normalized power factor. Yes.
Is there a relation between the normalized power factor and the power efficiency?
They are related because they do have what? They do have one term in common, which is what? Which is the maximum RF power. Are you following me on that? The maximum RF power is the same in both cases. Notice, by the way, why do I say maximum here? Why do I say maximum RF power? This signal, this, does it have to go to VDD? This one here, the RF signal, does it have to go to VDD? Remember what I told you a moment ago. This voltage is what? It's VDD minus what? L di of t dt. Agree? Does this point, does it have to go to VDD? Or it's just the maximum? It's just the maximum. It does not have to go to VDD. But the lower it is, the what? Less power is delivered. Did you get this or not? Yes or no? Okay, good. Now, let's see if you can help me with the class. Let me see if you can help me with the class B. Answer me the following question. What happened? It's same circuit, by the way. The circuit. It's the same circuit. Same circuit. However, in this circuit right now, we will see that this one is what? Is needed. Are you following that? This one is needed. Clear? We will see why in just a second. Tell me first, let's look at the input. No, let's look at the output characteristic first. Tell me, what did I do? Look at the load line. Look at the load line. This is now the load line. And where did I bias my current? Where did I bias my transistor? I biased it in where? At VDD, not in the middle of, in other words, the load line did not extend all the way to what? To VDD. The load line only extended to what? VDD. I still biased what? My transistor in VDD. But at VDD, there is no what? There is no current. Why? Because I am below the what? Below the threshold. You lost. What is these lines? What is these lines corresponds to? VGS. Are you what? You lost me here. Then why do you say the prerequisite of the class that you must have taken courses in electronics? Didn't Aaron go over this? Did Aaron go over a review of, huh? So help me, please, help me. Do you remember these curves? What is this? This is the input characteristic. What is VT? Can you tell me what is VT? VT is the V threshold voltage. Yes? The voltage at the gate needs to be higher than what? Than the threshold voltage. Why? Why? So that the what? That the N channel, for example, or the P channel, depends on the type of the mode that you are using, needs to be what? Created. Are you induced? Clear? For the electrons to pass from what? For the electrons to pass from the source to the what? To the drain, which means the current is in the other direction. Where am I biasing my class A, the one that we just finished? I am biasing it here. Yes? And where is the RF signal? Can you show me where is the RF signal? I am biasing my current here. Sorry, I am biasing my gate here. And where is the current? If I'm going to sketch this, then what do? This is the VGS. All of it is above what? All of it is above what? Threshold voltage, which means the MOS is always what? Conducting. How many degrees? 360 degrees. Did you get my point or not? Yes or no? Tell me, where am I biasing the transistor here? I am biasing it as what? As the VT, which means what? When you apply the RF, the RF will be around what? VT. Yes? What does it mean? This one is okay. Is this one okay? No, this one is not okay. Are you following me or not? Now see what happens. See what happens. This is the output voltage. Yes? Is it sinusoidal? It is sinusoidal. You agree? Yes? But how about the current? Is it sinusoidal? No, it's not sinusoidal. So what do I have? Look at it. Remember, you are projecting this on the load line. This is the load line. You are projecting this on the load line. Agree? This one, where is the load line during this? There is no load line. The load line is what? Is zero. Yes or no? Where is the current here? Can you show me the current? The current is zero. There is no current. Why? Because the transistor is in which mode? In the cutoff mode. Are you following me or not? Where in the characteristics? Where is it? Where is the cutoff mode? Is it here or is it here? It's here. Are you following me or not? Below the what? Below this line. Yes? Losing me? You lost? Did you lose me? Silence. The silence of the lamps. I'm a little bit concerned because what is the point? I mean, if you are losing me, what is the point? Can you concentrate a little bit? Can you concentrate? What are these lines? These corresponds to what? VGS. Yes? Let's start with what? VGS to be what? 0.5. Which is what? Let's say it's the threshold. Anything below the threshold, there is no current. There is no induced channel. Are you following me or not? There is no induced channels, which means what? There is no current. The transistor is what? It's in the cutoff. Are you following me or not? Yes? Okay. So, what do I have? I add this one here. During this cycle, which is how many degree? How many degree? 180 degree. What is the current? Zero current. Yes? Okay. Now, during this cycle, yes? By the way, during this cycle, what is it here? Can you show it to me here? This one will be here. Did you get? In other words, if you sketch the line like this, during this cycle, you see this cycle? This one is what? Is this one. Yes? Which is what? Above the threshold. And the transistor will be operating and the current will be like this. What am I getting? By the way, is it periodic? There is hesitation which is troubling me. You hesitated. Is this periodic? Is this periodic? This periodic. This one also is periodic. But is it a sinusoid? It's not a sinusoid. Think about it as what? Half-wave rectified. Did you get this or not? Half-wave rectified. But can I represent it by a Fourier series? Which means what am I getting? When I represent it by a Fourier series, what can I get? I can get the DC. Does it have a DC component? Question. Will the DC component be the same as the quiescent point? Why? Where is the quiescent current? Can you show me where is the quiescent current? This is the quiescent point. Yes? What is IDQ? 0. You're lost in translation. Okay, because you don't have background in electronics. That's the problem. Okay, concentrate. Where is the quiescent point here? The operating point. Where is it? This point. What is the coordinate of this? Can you give me what is the coordinate of this? It's VDD, comma what? 0, comma 0. The current here is 0. But does it have DC? It has DC. How do I get the DC component? I get the DC component through the use of what? Finding the Fourier series coefficient at omega equal to what? 0. Like we did earlier in the semester and in 301. Yes or no? Question. What is this? That's IDP. Yes? The peak current. Is it the fundamental? Is this the fundamental? By the way, now you have no excuse because a moment ago we were talking about circuits and you tell me most of us are systems. Yes? Now we are talking about systems. Fourier series. Is this the fundamental? What is the fundamental? When we say fundamental, what is the fundamental? Fundamental is the what? It's a sine wave. Yes? At what frequency? At omega 9. Does this one have harmonics? It has harmonics. This is not a single frequency. It has harmonics. Guys, yes or no? Guys and gals, yes or no? This has harmonics in it. Yes? When you expand this. By the way, do you still remember how do you get the Fourier series coefficient? How? Let's see. I'm still waiting. For the example, for the DC, I don't know what did we call it. We called alpha sub 0, for example. What is it? It's 1 over the what? The period. Yes? T integral minus T to T of what? F of T dt. What is this F of T? The periodic signal. Yes? Does this ring a bell? Okay. What is the alpha 1? It's what? 2 over T. Yes? Integral from where? And what is this? Sine or what? Sine or cosine, depends on what, whether it's odd or even. Sine n omega naught t. This is alpha n. What is alpha n? The nth harmonic component. Yes? The nth harmonic component. Does this ring a bell or not? What did we call this Fourier series? That's the trigonometric Fourier series. Agree? Agree? Have we seen this before? So my question to you is what? This value, IDP, is it the peak value? Is it the same as the fundamental value? It's not the same as the fundamental value. It's not the same. And I will show you that in just a second. Clear? Okay. Now, I'm not sure, but I'm struggling here. So concentrate. What is the angle of conduction? 180 degree. Keep that in mind. It's 180 degree. Half cycle, half a duty cycle is not conducting. Half a duty cycle, it is what? It is conducting. Clear? Okay, so now what do I have? Oops. What is it? What is the drain current? Let's see if you can tell me what is the drain current. Now, first of all, can you give me equation of the drain current? What is ID? Remember the in general. One more time. What is the drain current in general? It's IDQ plus what? IDP cosine. Yes? Okay, help me. Help me. What is the IDC? Where did I write it a moment ago? Here. What is the alpha? 1 over the period. What is the period? 2 pi. So it's what? 1 over 2 pi. But why am I integrating only from pi to 2 pi? It's because from 0 to pi, the current is equal to what? 0. Now tell me, where did this come from? What is the IDQ? 0. So what do I have? IDP times cosine or sine. Did you understand that or not? Okay, so let's use sine omega naught t here. What do I get? I get IDP over what? Pi. Did you answer where this came from? Yes or no? You just integrate this. By the way, to make things simple, replace omega naught t by what? Theta. So it's what? Sine theta, d theta. Did you get this or not? Yes or no? You get what? IDP over what? Pi. One more time. What is the IDP stands for? What is IDP stands for? The peak drain current. Which one? The AC or the... That's the AC. You follow me or not? Yes? But in this case, it's the same as the peak ID current. Why? Because the IDQ happens to be equal to what? 0. Yes or no? Okay, good. Now, what is the fundamental? What is the fundamental component? It's what? 2 over 2 pi. Did you answer where this 2 over 2 pi came from? I don't know where I wrote this, somewhere here. Hey, 2 over t. Yes? So it's what? 2 over 2 pi, the integral. From where to where? Pi, 2 pi. What is this? This is the same as this, but what am I multiplying it by? Sine omega naught t. Why? Why? This is this one. This one. With n replaced by what? 1. Because I'm interested in finding what? The fundamental. Yes? Cannot hear you. Question, before I continue. What will happen to the second harmonic, third harmonic, fourth harmonic? The third and the fourth harmonic will be what? Now, do we need the tank circuit or we don't need the tank circuit? We need the tank circuit. That tank circuit needs to be tuned to what? To omega naught, which means what? At all the other harmonics, I want the tank circuit to behave closely to a what? To a short circuit. Notice you said, I said closely. Why? Because this is a tank circuit. It is tuned at a what? At a singular frequency, which is a fundamental. What is it, by the way? What is it equal to? 1 over square root of what? LC. You follow me or not? But that's just one frequency. Did you get this or not? I want the behavior of this to be very close. In other words, to present a very small impedance or very high what? Admittance. Admittance is the opposite of impedance. Very high admittance at what? At the harmonics. Did you get my point or not? So all the harmonics will come in here. What comes in here is the what? Is the sinusoid. What am I trying to get here? What is the what? What is the peak of the sinusoid? Not what is the peak of what? Of the half sinusoid. Did you get it or not? I am trying to find what is this periodic signal? I'm going to break it into what? Into the DC component, fundamental, harmonics. I am only looking at what? The fundamental. I would like to see what is the peak value of the fundamental, not the peak value of this guy. Yes? The peak value of the fundamental, IDP over 2, half of this. Did you understand what I just, or not? From this equation, again, simple equation, this sign, by the way, this one by inspection, you can tell. Why? Because the sine and the sine will become what? Sine square. Sine square is what? 1/2 minus 1/2, whatever, cosine twice the angle. Yes? The cosine term will be equal to 0, and you get what? The 1/2, you end up with what? IDP over 2. Clear? Answer me the following question. What is the fundamental power delivered to the load? I'm still waiting. What is the fundamental power delivered to the load? First of all, answer me the following question. The current, let's start with the voltage first. The voltage across the load, is it sinusoidal? The voltage, one more time, the voltage across the load, which is what, by the way? Where is it? Show it to me. Remember, this is a what? An AC coupler. Is the voltage here the same as the voltage here? Yes, it is. Is it sinusoidal? Oops. Is it sinusoidal? I don't worry about it. So what is the fundamental component? VDP. That is the voltage. And what is the value equal to, by the way? What is the value? It's VDD. Agree? Okay. The current delivered to the load, is it fundamental? Sorry, I said, is it fundamental? Is it sinusoid? No, it's not sinusoid. Which one is delivered to the load? Just the sinusoidal component, the fundamental. In other words, when I expand this into a Fourier series terms, I only pick the what? I only pick the fundamental. Did you get this or not? Okay. Now, one more time. What is the power delivered to the load? Question number one. How come I have square root of 2, square root of 2? That's the RMS. Okay. Where is this 2 coming from? This is from this guy, IDP over 2. Yes? And what is this? That's the VDP. Why? Why? Because this one is already what? A sinusoid. Yes? Okay. Now, what is the VDP? And so, first of all, what is this? IDP, VDP over what? 4. Over 4? Yeah, over 4. Square root of 2, square root of 2. Yes or no? Okay. Now, for maximum efficiency, what is the VDP equal to? VDD. Why do I say for maximum? Does this one have to go to VDD? Could it be like this? It could be like this, but then you are not going to get the what? The maximum efficiency possible. So maximum efficiency, VDP equal to what? VDD. What is the DC power? I'm still waiting. What is the DC power? First of all, what is it equal to? What is the DC power equal to? It's equal to VDD times the what? The DC current. Not the quiescent current. The DC current, which is what? IDP over what? Pi. Yes? So it's what? IDP over pi times what? VDD. Cancel, 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 cancel. You end up with what? Pi over 4, which is what? 78.5%, roughly. 78.5%. Did it improve? Why? Why did it improve? There is a reason for it to be improving. Why? Because during the what? When the transistor is cut off, there is no current passing through who? The transistor, which means what? Half of the time, there is no power what? Lost. Did you get this or not? Yes or no? So the efficiency improved a little bit. Clear? Clear? Okay. By the way, all of this equation, we can derive, as I will show in just a second, a general equation that applies to all of them, to all the classes. But I wanted to go one at a time so that you can see it before I dump on you the general equation. Clear? Okay. Now, clear? Okay. Class C. I need to make sure that this is in because I forgot to number them. 1 second. By the way, this is after you sketch. This is after you find. By the way, what is the maximum efficiency? This is the efficiency. What is the maximum efficiency? 78.5. What is this? That's the DC power. What is this? This is the AC power. Yes? And what is this? That's the power dissipated. Power dissipated, remember, is equal to what? It's equal to the DC power minus the what? The R power delivered to the load. Clear? How come this one, all of it is divided by RL? Because that is the load. Are you following me or not? The power delivered to the load is what? Is the voltage square divided by what? Divided by RL. Clear? Okay. Now, class C. Same circuit. The circuit means what? Here. What am I changing? I'm changing the biasing. Are you following? I'm changing the bias. Now, for class C, the need for the tank circuit is even what? More crucial. Are you following? You need to have a tank circuit. Clear? I wanted to see what happened. Tell me what happened. Okay, first of all, let's look at this guy. What is this? This is the input characteristic. Where am I biasing my transistor? Where am I biasing my transistor? I am biasing my transistor below the threshold, which means what? If you sketch the sine wave, only during this portion of the cycle, the transistor will be what? Conducting. And the rest of the time, the transistor is what? Off. Did you get my point or not? So what do you get? Look at the current. This portion here is this. This portion is it. By the way, is this periodic signal? It's still a periodic signal. But it is now, remember in class B, it was what? Pi to what? 2 pi. Now it's even what? Less than that. So the conduction angle, in this case, alpha, is less than what? 180 degree. Did you get this or not? Okay. We will see in just a second that when alpha approaches 0, what does it mean, alpha approaches 0? It means what? It means the transistor will what? Not conduct. Yes? We will see the efficiency approaches what? 100%. Yes? But on what expense? On the expense, there is no power delivered. Do you understand that or not? There is no power delivered. What power? When I say power, what power? The RF power. There is no power delivered. Why? The power is applied at the input. And if the transistor is always off, there is no RF power at the output. So when we say efficiency equal to 100, what does that mean? Did you get my point or not? I will show you that in just a second. Now, show it to me here. Where did I bias? By the way, you see this VDD now? It's still VDD. This one is still VDD. But now the load line is what? Is below it. Which means what? What does that tell you? The IDQ. What is the IDQ? IDQ is the quiescent what? Current. Now what is it? Is it negative? It's negative. Remember in class B, what was IDQ? 0. Now I'm going even what? Lower. So the IDQ, the quiescent current, is what? It's negative, resembles a negative stuff. Did you get this or not? And you can see, by the way, is the input is still, is the output voltage is still a sine wave? The output voltage is still a sine wave. By the way, the output voltage, when we say a sine wave, always remember, we are assuming the approximation that the saturation voltage of the drain source saturation is almost equal to what? 0. If it's not 0, you are not going to get a clear sinusoid. Yes? But the current is still what? The current is no longer what? It's no longer a sine wave. Is it half sine wave? No, it's not half sine wave. It's what? It's even lower than that. Are you following? The alpha here. Clear? Yes or no? Okay. Let's set up the general equations. So in other words, all of this now, this one applies to all of them. In other words, if we did not go through just this one here, we would get the same result, as I will show in just a second. Let's see if you can help me. So this is the general derivation of a power efficiency, power amplifier efficiency. Remember, when I say a power amplifier is the what? Is the constant time. Okay, let's simplify first of all the notation. Let omega naught t equal to what? Theta. So I don't keep repeating omega naught t, I just call it what? Theta. Let alpha be the conduction angle. What is alpha for class A? 360. Class B? 180. Notice, by the way, class AB, which we neglected, is somewhere in between. It's in between 180 degree and what? 360 degree. Yes? Okay. Oh, I will not discuss AP. Okay, let alpha be the conduction angle. So what is the theta? The theta is between, let's say symmetric, between what? Minus alpha over 2 to what? Alpha over 2. Did you, for example, if alpha is equal to what? 360, what is this? From minus 180 to what? 180. That's 360. Did you get this or not? Okay, good. For class A, this, here. Now, help me. What is the drain current? What is the drain current? I'm using this equation, general equation. This is the drain current. Yes? What is it? It's IDQ plus what? IDP. One more time. What is IDP? It's the peak current. Peak drain current. Yes? Notice what? IDP times what? Cosine theta. Did you get this or not? Cosine theta means what? Cosine omega naught t. I just write cosine theta. Now, for alpha greater than pi, what is the IDQ? Positive. Which is which case? When alpha is greater than pi. It's the case of what? Anything above b, which means what? AB all the way to what? A. IDQ is what? It's positive. For alpha less than pi, IDQ is what? Negative. For alpha equal to pi, IDQ equal to what? 0. From these results, what do I get? I get IDQ is equal to minus IDP cosine alpha over 2. Let's see if you can help me here. If alpha is a 360, what is cosine 180? Minus 1 times IDP minus IDP. IDP, which means what? It means IDQ, which is here, is almost the same as what? IDP. Yes or no? Okay. If alpha is equal to pi, which is class B, what is cosine pi over 2? That's 0. If alpha is less than pi, the cosine is what? Positive. With the negative becomes what? Negative. Yes or no? Okay. What is the DC? What is the DC? The DC is the equal. The DC is what? 1 over the period, integral, minus t to t, the function. Yes? What is the function? The total current, which is the drain current. So what do I have? IDC equal to 1 over 2 pi, that's the period. How come this is minus alpha over 2 to alpha over 2? That's the conduction angle. Yes or no? In the case of class A, what will it be? From minus pi to what? Pi. Yes? By the way, could I have used from 0 to pi? All what you need is what? It's one angle. But I thought that if you do it symmetric minus to plus, it becomes a little bit clear. Clear? Okay. Help me. Where did this come from? This term. In the place of the IDQ, this IDQ, where is this IDQ? I plugged here. Yes? The IDP is common. I get it outside. Sorry. What do I have here? One more time. IDP cosine theta, which is this, minus IDP cosine alpha over 2 d theta. Did you get this or not? No response. Okay. You integrate this, simplify a little bit. You end up with this. That's a DC current. Clear? Let's check just to make sure that it's the right equation. Class A, what is the alpha? 360 degree. Yes? What is this? 0. What is this? Minus 1. 2 pi. With this 2 pi. And what do I end up with? The DC is the same as what? IDP. Yes or no? Yes. Why? Because the current is a what? Is a fundamental. So the DC is the same as what? The quiescent current. Class B, alpha, pi. Yes? So cosine pi is what? Is cosine pi by 2 is 0. So this one is gone. 1. Cancel. And what do I end up with? IDC equal to what? IDP over what? IDP over pi. Did you get it? No response. Okay, good. So, why am I calculating the IDC? Why am I calculating the IDC? I'm calculating the IDC to get the average DC power. Clear? Say the DC power. Why do I say average DC power? I'm sorry. Remove the DC power is what? It's VDD times what? IDC. Yes? Why VDD? It's getting from the power supply. The DC is coming from the power supply. Yes? Now, how do I get the harmonic, nth harmonic? By the way, in a minute, we will substitute n equal to 1. This is the nth harmonic. What is it? 2 over 2 pi. And instead of what? 1 over 2 pi. It's 2 over 2 pi. This is the same thing, which is the drain current, but I'm multiplying by what? Cosine n theta. Not n alpha, n theta. theta is the what? Is the omega naught t. Is times what? D theta. Now, if you plug in n equal to 1, by the way, can you, from this equation, can you get the second harmonic? You just plug in what? N equal to 2. Are you following or not? By the way, if there is no tank circuit, and the question tells you what? Find the power in the second harmonic, which will be, by the way, a loss, because it's not going to be what? It's not going to be what? Radiated. Do you understand that? You just calculate that and multiply by the mole. Clear? Okay, help me. If you plug in n equal to 1, this is what you are getting to get. Yes? It's simple integration. Simple integration. This is the what? The fundamental load current. Is it the same as IDP? Not necessarily. Let's see. In class A, what is the alpha? 360. Sine 360. 2 pi. I messed up? 1 second. No, there is a 2 here. There is a 2 here. How could it be? There is a 2 pi here. This 2 pi. I forgot the 2 pi here. Why? Listen to me. Alpha equal to what? 360. What is sine 360? What is this? 2 pi. We cancel with this 2 pi. I get what? The fundamental equal to what? IDP. Okay. For class B, what is it? 180. What is this? 0. What is this? Pi. And the pi cancel with this one. I end up with what? IDP over what? What is this? IDP over 2. Clear? So this one should be 2 here. Okay. Now, what is the R of power? What is the R of power? This is the fundamental load current. Yes? What is the R of power? It's what? VD. Why is this one VTP? Sorry. Why is it VDP? Because the voltage is what? Sinusoidal. The voltage across the drain to the source. Source is grounded. The VDS is what? It's sinusoidal. Yes or no? Okay. So VDD times what? IDP over 4 pi times what? Alpha minus what? Sine pi. Clear? By the way, you can see why this one is missing. Because this is 2, this is 2, it became what? 4. Yes? Question, why is this 4 VDD? Why is this VDP equal to what? VDD? That's for maximum efficiency. In other words, does this have to be VDD? It does not have to be VDD, but for maximum efficiency, it's VDD. Yes? Now, what is the efficiency? The efficiency is this R of power divided by what? The R of power divided by what? The DC power. I cancel the terms that are common. Now, I want you to see this. Let alpha approaches. First of all, alpha equal to 2 pi, class A, you will get 50%. Do I need to show you this? One more time. 2 pi, 0, 2 pi, 2 pi, 0, 2 pi, minus 1 times alpha. You get 50%. Yes? 78%. I want you to tell me what happens when alpha approaches 0. When alpha approaches 0, what is the numerator?
0.
What is the denominator? No, the denominator is also 0. You are not seeing it. Why? There is an alpha here. You follow me or not? I think you missed this alpha. This cosine 0 is what? It's 1, but it's multiplied by alpha. Yes? And this one is sine 0, which is also what? So you have 0 over 0. What do you use? That's the Hospital's rule. It's not the hospital rule. The Hospital's rule. Did you get what I'm saying? How do you know how to use the Hospital's rule? You take the derivative of the numerator, divided by the derivative of the denominator, you put then alpha equal to what? 0. This is what you get. Impressive or not impressive? Not impressive. Why? I wanted to see one thing. This is the R of power delivered to the load. Yes? When alpha equal to 0, what is it? 0. You are not delivering anything to the load. So you are operating at what? 100%, but you are not delivering what? You are not delivering any power to the load. Did you get my point or not? So that's the trade-off that you are going. Increasing the efficiency result in what? Reducing the amount of power that you are delivering to the what? To the load. Clear? No response. Clear? Clear? Okay. Now. Question?
We have about 5 minutes left.
Oh.
Just a heads up.
Okay. Now, before we get back to by the way, in the chart you can read it on your own. So this, all of these equations, you can read all of this analysis. I went through it, all of this. You can read it, class efficiency. And the efficiency, we calculated this. This is, by the way, a push-pull. You understand what push-pull means? Okay, 2 transistors. Yes? One of them is what? One of them is operating, the other one is operating. But I will leave this when we get to the switching amplifier, because switching amplifier have something which is very similar to this. So I will leave it when we get to the switching amplifier in a minute. This is class C. By the way, you notice more than what? More than 50% or more than half the duty cycle, the transistor is what? It's off. Yes? Okay, good. Now, the voltage is still what? It's still a sinusoid. That's the voltage. It's still a sinusoid. But the current is no longer a what? A sinusoid. This equation, I just showed you this, all of this here. And this is the efficiency curve that I just showed you. Okay. And this the problem that I just explained it to you. Now, listen to me. Let's see if you can help me justify the use of the switching amplifiers. The switching amplifier, let's see first of all, what are the problems for the power amplifier? Efficiency is low, and it depends on the amplitude of the output signal. What does that mean when I say the amplitude of the output signal? What does that mean? What it means is this. Remember I told you that this one cannot reach more than what? VDD? Not the maximum, the fluctuation. In other words, this cannot go. See, what is the RF power depends on? At the output, RF power. Does it depend on this? Yes, it does. The question then becomes the following. Can I make this exceed VDD? Not sure did you understood my question. Did you understand my question? You did not understand my question. This is 2 VDD. Do you understand what the 2 VDD is? Yes?
The time is 14 o'clock.
Can this one go up more than 2 VDD? But you have to remember one thing. In here, I am assuming that the voltage is what? Sinusoidal. Yes? What if the voltage was square wave? Instead of this, what if the voltage was a square wave changing from 0 to VDD, to 2 VDD? You are losing me? You are losing me. Switching on, off, on, off. I'm going to get a square wave ranging from what value to what value. And instead of a sinusoid, it's what? 0 to 2 VDD. Yes? Is that a sinusoid? That's not a sinusoid. But can I represent the square wave as a sum of fundamentals plus harmonics? I can. The fundamental, by proper choices of what? Of the parameters, can go more than what? More than the square. In other words, what I'm trying to tell you is the following. Let me show you. Do you see this? These are what? These are the different harmonics. With the proper choices of the voltages of the third harmonic, second harmonic, or third harmonic, you can get the first harmonic to be more than what? The square. Did you get this or not? Which means, oh, by the way, we are only interested in the fundamental component. Yes? Now you might say, but you are going to generate the harmonics. The harmonics, just like the tank circuit is getting rid of the harmonics in the current, let it get rid of the harmonics in the what? In the voltage. Did you understand that or not? What is the ultimate thing? I'm running out of time. Next time I'll show you. But what is the ultimate thing? The ultimate thing is the following. I do not want any power dissipation in the transistor. Which means what? It means I would like the voltage across the transistor and the current through the transistor not to be what? Overlapping. Do you understand what not to be overlapping means? Means if there is a voltage, I want the current to be what? 0. If there is a current, I want the voltage to be what? 0. So that when I multiply the voltage with the current, I get what? I get 0, which means what? There is no power dissipation in the what? In the transistor. And all the power of the DC will go to the what? To the RF. You lost me? You lost me.
Professor?
Yeah.
It's about, well, I'm out of time.
And my kids lost me anyway, so we will continue next time. They lost me. Did you lose? I did, you did. But did you understand the common mode? Sorry, the constant current. Okay, good.
And this concludes EE 544 on Thursday, March 27, 2014.